All right, we'll go ahead and get started on the on the next talk. Sorry. So the next one would be radiation safety, shielding, and physics part two. So the last one was physics part one, some basics, and this one we'll talk a little bit more about some of the physics and how it interacts with the radiation biology. Uh, Talking about that one mainly because since this is envisioned also to be kind of a research park in collaboration. We'll talk a little bit about some of the where physics and biology kind of meet to be some interesting research in the radiation biology aspects. So since it's just after lunch and I know what everybody wants to do is do some very detailed math. So everybody ready for this one? So we can all stay awake. But just kidding, we're actually not going to go through these ones. But the first part I want to start with was the shielding aspect. And traditionally, the shielding for photon therapies in general use analytic equations like this, and even some early proton type shielding and some of the initial measurements that people got when we talked about things of being 5 meters thick and such kind of comes from some of these equations. And the first thing to know really about radiation protection and radiation shielding is we're always extra conservative. So we want to make sure that the things are right. We're building something, particularly anytime there's things with regulatory, and we had the regulatory discussion earlier. And when people see things like big fines and jail time and things like this, people get a little bit nervous and want to make sure that what they do with the radiation aspects are extra safe, which is very important, but as we see, can sometimes lead to some detrimental things. So modern, meaning anything in the last maybe at least 15 years, for sure, last 10 years, particularly for a proton or a carbon center, your radiation calculations should all be Monte Carlo based. So you'd only use these equations as a kind of a rule of thumb if something looks kind of odd to double check yourself. Before we talk about really the radiation shielding for a particular center, sometimes I like to put things in context a little bit. So, radiation shielding, radiation safety, particularly those of us that are in the medical radiation therapy atmosphere, whether a radiation oncologist or medical physicist stuff, when I think about radiation shielding, like shielding making the room right for the LINAC so there's no radiation outside for photon machines and such. But really, it started when you had these first particle accelerators of, how are we going to do the shielding? And honestly, it was always that shielding was actually more of a secondary thought than the primary thought. And, first you have to actually build these accelerators, try to figure it out, and then realize, oh, we got to somehow block these. The second thing to kind of remember about this is in many physics labs, when we talk about early radiation therapy, particularly particle therapy, they were offshoots of physics labs. I mean, there was an accelerator already existing to do some nuclear high energy physics. And they said, okay, after it kind of lived its life doing the physics experiments, what else could we use it for? And say, oh, well, we could use it for this radiation type treatments that might look interesting. And in those labs, really, and if you go to any kind of modern large university type labs or anything like that, you usually have this modular shielding where you bring in essentially big concrete blocks kind of on a crane and put them in where you need them, because you're always going to do something different. Your experimental beamline that you have set up, you'll want something different, so you might need a different amount of shielding. So here's some very early ones, back from doing shielding in 1959, etc. But again, just kind of seeing that they would usually build the thing and then, as a second thought, realize, oh, we need to shield it for radiation protection. What about for particle accelerator? So here's here's the Loma Linda. So when I talked about that history of particle therapy, one of the first hospital-based Here's 1990 kind of, and what's shown here is some of the thicknesses they had in the walls. And here's another one from 2015 in South Korea. And if you take a quick look, particularly in between rooms and stuff, they things haven't changed much. And really, when you look at this, you'd wonder why are they still about the same thickness? And I'll talk about that in a bit. But if you think about this one here and the things from like 1990, basically up to 2015, let's say, uh, most of those particle facilities, whether it's proton or carbon, were double scatter. And in the previous lecture, I actually kind of skipped over all the double scatter stuff because it was already lunchtime, and no one really does double scatter anymore. But that kind of a system makes a lot of neutrons. So when you're doing particle therapy, you're really shielding for neutrons. And that's double scatter. What they're actually doing is blocking a lot of the protons, and that creates a lot of neutrons. So you needed really thick walls because you were actually almost purposely generating a lot of neutrons. So that's why the earlier ones, having all these thicknesses were really needed. Uh, and here's another. This one again. This is from Mid-Austron. Well, this one here is HIMAC, the one in Japan. This is from 1994. You can see they have a bunch of synchrotrons and different beam lines. And again, they start with carbon with double scatter. And here's a carbon proton system. This is a Mid-Austron one. And they also have really thick walls. But interesting with theirs, their thick walls, they were kind of a honeycomb. So what it is actually concrete filled in with dirt. And particularly their soil there actually has a lot of iron, relatively. So it actually acts as a decent shield, but it's thick because it's not all concrete. It's a little bit of concrete with a lot of dirt. So it's kind of also important when you kind of go and see these things you realize their walls are really, really thick. Well, because they're actually not all concrete. They're mainly dirt in there. Okay, so in a bit, I'll talk about all the calculations it's going through, but that was kind of overview just to see that traditionally walls were really thick, and they were really thick really because of that double scatter. So I'll concentrate a little bit about the US regulations, and just very similar to the discussion earlier about the regulatory here in Thailand, there actually isn't much difference. Didn't actually talk about the measurements and the units and what the actual restrictions are, and I'll go through that a little bit. But in the US, there's a regulatory body, and they set out certain rules, and then just like here, then different organizations are the ones that kind of implement those rules and follow. And essentially, they regulate radiation materials and radiation generators, very similar to what's done here. And in the United States, we have within the states have actually the authority over the ones that produce the generators, and they usually default to kind of the national regulations as guidelines. But there are, just like everywhere, many different layers of regulatories and people that you end up having to deal with. And there's always, locally and maybe even here in the city of Bangkok or in certain region, there may be special rules that you may have to comply with and such, given whatever population density or things like that. So knowing exactly what's set up is important in order to follow the guidelines, because particularly as, for example, one of my responsibilities, ultimately someone is responsible. So it's someone's signature that signs this that says it's complying or it's built to comply. And in the US, it's usually the medical physicist. So me being the chief of medical physics for the carbon center that we're putting in the proton carbon center, ultimately it's my signature to say this is properly shielded, this is probably everything else, and then the regulatory are the ones to go in and check this one. So if someone's on the hook, that would be me. So there's different organizations. So we was talked a little bit earlier today about the IAEA, and so they're not a regulatory, but they put out guidelines so that maybe at least across the world we're somewhat uniform in the rules that we follow, and making sure that in general that we are doing good under radiation protection. So that's the international organizations, ICRU, ICRP, IAEA. Then, of course, in the U.S., we have our own national organizations. So NIST, the National Standards Institutes, and then recommendations from like the American Association of Medical Physicists and such. So all these, give inputs and such, and sometimes there could be, so many different things of what to follow. But and then there is a certain, set of rules and guidelines that need to be followed. The main thing in, earlier when the secretary was talking about, this organization and saying, for peace and prosperity, also being that the regulatory body shouldn't be the one just saying no. It should be the one that's kind of helping, following the rules, but helping the organizations or the companies or the hospitals, whatever it is, meet the rules and how to go about them. So there should be, in general, no practice should be adopted unless it introduces or produces a positive net benefit. So setting up a rule that basically just says no doesn't benefit anybody. It stifles. So making sure that the rules are set up that the public is protected, but you're able to progress the science forward. In general, the ALARA principle means as low as reasonably achievable. And, you have to take into account different factors, economically, because you can make things very, very safe, let's say, on radiation shielding, but at the expense of making it almost impractical to build a certain type of building. And also social factors. Maybe you need to be extra low because you're going to be near an elementary school or something else, so you take extra precautions just out of safety, even though you meet the regulations. Maybe you do something a little bit extra. And of course, comply with the actual, dose limits, which we'll get to in a bit. So those are more of the philosophy behind, regulations or how they should be perceived. So here's, some of the numbers, because I always like, well, what does it really mean? First, there's generally, controlled areas and public areas. So controlled areas is, we know there's radiation that's going to exist there. We have monitors up, etc. Any other personnel, if we think they might get more radiation than is standard, they wear badges, etc. So those are controlled areas. Ideally, we would minimize the amount of controlled areas, right? We don't want the whole hospital to be a controlled area. We can't be badging everybody and doing things like that. So trying to focus on where the controlled areas is. And then the other ones is the generally public access, so kind of uncontrolled. So as far as area, the primary design goal, limiting the dose equivalent rates 30 cm beyond the shielding barrier to less than 20 microsieverts per area in all the areas. So that's our primary design goal, to get to that level. Secondary is within the controlled areas, you have these things that are, per week or per year. And for the controlled and uncontrolled. And just putting that into perspective, let's see, there's the laser. Okay, it's working. So 1 microsievert per year in the uncontrolled areas. Well, when I flew here to Thailand, I got about 0.1. So, when I fly back, I'd be 0.2. So if I come and visit here 5 times, then I've already kind of exceeded that. So sometimes it's good to put those into perspective, how much we're actually talking about here compared to background or compared to something that is maybe slightly outside normal, maybe flying 5 times to Bangkok and back, maybe not quite normal, but, is realistic. So again, putting it into a perspective of what these numbers actually mean. And again, these are like per year, sometimes per week. And later you see the thing that's really is this one is the per hour. That's really kind of the important part, because usually no one is standing in a certain place and getting all that radiation in 1 week or 1 year. So really that per hour is the one that is important. All right, so this is coming back something, as you see here, kind of how a vendor must provide. So now let's talk a little bit about the actual process of coming up with a design for shielding. So there's beam loss points, and this is something that the vendor has to provide you. And it's good to understand what the vendor is actually providing and how their system works. Again, because if you go back to the regulatory, there's, if you think of it kind of incentive wise, the incentive on the vendor side when they give you these numbers is to make them as big as they could possibly be. Because they don't want to be accountable to say, oh, wait, we messed up. It was actually, 10 times bigger than we gave you, because then they're responsible. So understanding, and you'll see this in a bit, understanding how their system works and making sure the numbers that they give you are actually realistic. Because if they give you things that are one, factor of 10 too small, well, then you can't do a proper shielding design. But just as bad, if they give you numbers that are 10 times too big, then, or in some cases I've seen where they've given numbers that may be 100 times too big that are not realistic, what that causes you as the person receiving the equipment and designing the building, etc., is you spend a lot of extra money in shielding that you wouldn't really have to. So the vendor has to provide you their loss points, but it really is incumbent on the one receiving that information to make sure that they're actually realistic. We talked about this a little bit, but the beam consists, or the beam line consists of four major regions. So here, what I'm going to end up showing is when you're doing this shielding design, and talking about shielding design, the way we're spending time on shielding is because that's directly related to the regulations, right? The regulations are going to put out certain numbers like that X number per week or per hour. So it's up to the country or whoever is responsible for setting the regulations to set those numbers. And they should be consistent, right? There's no reason that that number is going to be any different for a proton center or a carbon center than it is for a photon center or anything else, right? It's really at the end point, how much dose does a worker get and how much dose does the public get? And you want to protect against that. So nothing necessarily special to, as far as regulatory, as far as limits to say about a particle facility than a standard facility. But the thing to take into account when you're doing a particle facility is there are different components as opposed to just a LINAC. And I don't know how many of you here have done a shielding calculation for a LINAC, or also done the acceptance for it. So maybe some of you may remember doing these things called the head wrap, where you put film all over the that LINAC to make sure that there's no point that there's that they're not properly shielding, etc. So it's not really feasible to do that for a particle facility. So you have to take into account each part. So there's the injectors that we talked about. So there's going to be a lot of loss here, but generally those are very low energy, and generally very low energy don't cause many neutrons. So there's not much shielding worry there, but you have to make sure. And then when they get injected in, we're talking before about the acceptance, the admittance and acceptance. You have loss, a great deal of loss points there. Again, those are generally much lower energy. So as far as the shielding and regulation, it's not that big of a deal, but it is important when you're talking about if a person is actually in here working and doing some tests on the system. Then you have the synchrotron itself. There's going to be loss points, particularly near the extraction. So we talked a little bit about you could have a cleaner extraction or a dirty extraction, these kind of things. So when you extract going down the beam line, you're going to have loss there too, because when you extract the beam, not all of it's going to come out clearly now into your beam and go down the path. Some of it's going to kind of get lost. And now that is generally higher energy. So knowing how the extraction is done and how clean the extraction is being done. Again, this is for a synchrotron system. I'll touch on briefly a little bit about a cyclotron system, but it's the same concept there. And then the beam line itself. So there's different parts, and then in the treatment rooms themselves, again, while you're treating a patient, the therapist or the physician or physicists aren't actually in the treatment room, they're in the control room. So you have to make sure, here we have a maze, and you have to make sure that you're properly shielded, that if someone is standing by the door of the maze, that they're not getting that much radiation. So knowing what energies are involved in each of these components, you need to take that into account when you're doing the shielding design. So now a little bit of maybe a picture that's a little bit easier to understand here. So this, what's being shown here in that color there is actually, so these are Monte Carlo simulations. I'll talk about it a little bit, but kind of showing the radiation dose. So again, the vendor, as you see, where you have the injectors and stuff, these are all low energy, so there's not much radiation actually producing there. But this deflector here, so at the deflector, this is kind of the thing that gets for a synchrotron system. And again, I spent a lot of time with synchrotron because I know that's the system that you guys are looking at right now. It actually does the kick, and you have a loss point there because that kick is what eventually gets the beam to kind of come out through here. So knowing how this is set up, getting the right location, and there's beam scrapers, there's different parts. So every system's kind of a little bit different, but you need these loss points, know exactly where they're located, and the vendor has to give you what their expectation is of what their loss is. If they have really clean extraction, that loss point may be smaller. If it's not as clean, maybe it's bigger. Then there's, different monitors along the way to check the beam, making sure it's doing what it's supposed to. Then obviously in the treatment rooms themselves. The ISO center for here in the gantries are kind of inside, so that's why right now you don't see the red, and here's the carbon. Maybe it's on the next slide. Yeah. So I'll just talk about one part here is, again, now when you're doing the shielding design, you have to really think about what your goal is. So we have the goals of doing the regulatory body has made statements such as it needs to be under X millisieverts per hour or whatever it is, or per week, whatever that regulation is. So now you have to interpret that regulation. Well, what does that mean when you're actually treating a patient, right? What does in any 1 hour mean? Well, how many patients I'm treating, etc. And also, when you're thinking about that, what does it mean when you're treating? Are you the patient right here? So as we saw with proton or carbon therapy, the beam is stopping inside the patient, right? That's the whole point, is that you have a bright peak and you don't have any of that exit dose. So when you do these simulations, you have to actually simulate, maybe not a patient, but some water there. Then you have to think a little bit, is there anything weird, like if you're doing a prostate patient that may have hip prosthesis in or anything metal? So kind of thinking about those things and do proper simulations to make sure there's not a case where you're unaware of something that may be causing a lot more radiation, particularly the neutron radiation, than you're expecting. So you have to take all into account when you're setting up. Now I'll talk about a little bit about how we set this up. So again, what's the goal is you could be really conservative and go back to that first slide where you just do these hand calcs. And those hand calcs are set up to be extra conservative, usually by a factor of 10, maybe even 50, because they're just really quick back of the envelope calcs and you always estimate up. To be a little more precise, you want to use a Monte Carlo simulation. And many people talk about Monte Carlo. Many people in this room and probably in this institution here have done a lot of Monte Carlo simulations. That's by itself isn't magic. I mean, it's like anything else. If you do it wrong, you're going to get a bad result. So you got to make sure you put good inputs in and do something that has been well tested. For this simulation, I use Geont 4. In nuclear physics, you can use MCMP, MCMPX. That's a really good. You're really concerned about the nuclear interactions here because neutrons is what you're interested in. You got to be able to take into account when you get this information. In order to do a good design, you got to take in basically CAD information because your architects, your designers are going to design something. You have to be able to check that. So making sure you can actually use those type of files. And then you have to do, those of you that have done any type of Monte Carlo simulations, you have to decide where you're going to actually do your scoring. because this is a big facility. You can't just score everywhere. You got to put certain points that you could do, measure the radiation dose, the radiation exposure at those things. So essentially just how you set something up. So overview, let's talk about here. I think this is an important process. So there's two ways you could go about this. Actually, obviously, there's many ways to go about it, but two primary ways. One is you basically get from the vendor has their standard setup. Here's a standard system, and you take that standard system. Your architects kind of fit it into the space you have, and then they say, okay, here we go, and they're going to build it, and then your radiation safety officer, your medical physicist, whoever's the one, or your shielding consultant, whoever has expertise in this is the one that does the calculations to make sure, for your system, it was okay. And then you're all good, and your regulatory body checks it and say, this is good. And then you turn on the beam and you do measurements. So that's one standard way of doing the thing. I'll say right now, the problem with doing it that way is one, usually any setup isn't standard. As Pi was already mentioned, I think in the location you're looking at right now, you're already boxed in with different things. So maybe you have to do something slightly different. And second, it's very inefficient in cost, because any space you use, any time you pour concrete, pouring concrete is expensive. Pouring a lot of concrete is more expensive. And if you pour so much concrete, that means that you have now less physical space for a treatment room or exam rooms, etc. So it's important to have a process to go around. And this is just the general about things, the interactions that can happen with neutrons. They like to bounce around. And the fluence from simulations involved with the conversion factors of beam losses. So this is where your vendor has told you for a certain area, this is how much we expect the beam to get out. Well, you have to, now they're accelerating protons. So they told you this is how many protons they expect are, just say, escaping right now, are being lost. Well, those are going to have to hit something. And when they hit something, now they create neutrons. And that's really the thing that you're shielding against, because neutrons kind of like to just go everywhere and kind of go through things. They're neutral, so they don't interact that much. So you have to kind of take all these into account when you're doing that design, that they give you a certain number of protons, but that's not at the end what you're actually calculating. So the typical shielding design process, your vendor gives you something, your architect kind of puts it in, your shielding consultant does a calculation and says something, and honestly, most of the time they come back and say, that looked fine, but maybe at this point you should make it a little bit thicker. And then that's their recommendation. And then you go and you build it, and then at the end you measure. So I really don't like that approach, because I'll tell you something very, very clearly right here. If I'm the shielding consultant, I would never tell you to make your wall thinner. Because why would I tell you to make the wall thinner? Because if anything, I'll tell you to make it thicker, because I'm just saying, the consultant, I'm going to say, be extra, extra safe, because I don't want anything to go back to me to later say, oh, wait, you told us that it could be only this thick and it needed to be thicker. So in general, the shielding consultant is never going to say make it thinner. It's always going to say make it thicker, or it's okay. So better way to go about this is more of an iterative. So it does take a little bit longer, but in the whole scheme of how long it takes to set up one of these things, it's not that much longer. It might take a couple extra months. But this is where you're going back and forth between the shielding consultant and the architects and the vendor. So first, your shielding consultant or your medical physicist should understand the system, so they can really have a meaningful conversation with the vendor and question some of their loss points. So I've seen some, like I said before, where their loss points were just inconceivably high. Like there's no physical way you can actually get that much of a loss. If you ran the system at 110%, 24/7, you couldn't make that much loss out. But again, they're going to say that because they're going to be extra careful because they don't want something coming back at them saying that, hey, you didn't tell us that it wasn't kind of high enough. And again, this all goes back because it's regulatory. And we saw earlier there's these things, some big fines and jail time. So everybody wants to be obviously extra safe and build things a lot bigger. But if you understand the system and have that conversation with the vendor to really get what the loss points should be more realistically, this includes the energy spectrum and such. And you have the conversation with the architects being able to iteratively design this and change the design and check different things so you can actually build the system and shield the system properly, but not wastefully. So that's what this kind of goes back, going through an iterative till you got the shielding that you desire to the goals that you've set out and you have. And with the architect, making sure you have the biggest footprint of usable space. Because again, thick concrete, X meter thick, that means that's how much less space you have for an exam room or anything else like that. And again, particularly here, you're probably going to be physically limited in your space. So it's important to have kind of this discussion and dialogue to go back and really actually design the building properly from also not only from a layout as far as patient flows, but also from a shielding perspective. And then this goes back to with the vendor that you don't only have their loss points, but also what are you actually doing for your treatments? So in proton therapy, particle therapy, like here to have. So how many patients are you going to treat in an hour? Because really at the end, the thing that drives the shielding is that in any 1 hour regulation. And how long are you going to treat? I'm going to assume here that you're going to treat probably 16 hours a day because you're going to have really high demand. And in that any 1 hour, or for a worker, does that mean they work 12-hour shifts? Or they 8-hour shifts, 10-hour shifts, these kind of things to go through? The other thing that's important is what is your fractionation? So we talked about that earlier, and you saw that currently the average number of fractions for the proton center here is 10. And this is now in 2023. It used to be, if you take an average, it probably used to be more like 30, and now it's going down 10. Are we ever going to go down where we're like 5 or 2 or 3? Is that where the research is going to go? So when you build the building, you're designing it now, let's say in 2024, but that building and hopefully that center will be treating for, maybe 25 more years. So it's 2024 now. In 2050, it may still be in use. Hopefully it's still in use. But it is the way you're treating now, the way you're going to be treating 25 years from now. And if 25 years from now is very different, it's going to be very expensive or infeasible to go back and try to add shielding here or there. So that's how come here being actually even more conservative, assume that every patient that's going to get treated, that they were going to get 1 fraction of 50 gray. Now we're probably never going to get to that point. But in radiation safety, you always kind of err on the side of caution. So did that. The other thing that's important is, well, how big of a volume are you being treated? So unlike photon therapy, in particle therapy, the bigger the tumor is, the more particles you use, right? So last time I said, a few trillion particles for a target. Well, if the target is really small, well, you use less particles. If it's really big, you use more particles. So you have to kind of estimate how big of a volume are you going to be treating? And the other thing that's not listed here is also which energies are you going to use? If you assume everything's the very highest energy, that's conservative, but now you're going to be conservative, but that means your walls are going to be even thicker than they really need to be. So you have to kind of take that into account. Still be conservative because it's radiation safety. You want to be conservative. You want to make sure things are good, but not overly so. When you're thinking of a LARA as low as reasonably possible, it's not as low as unreasonably feasible. So you got to really think about that and put the time in up front to save later. And in the iterative process, it does take little more time, but again, you get a little bit better result because you kind of go through this process of getting the 3D CAD from the architect, bringing it into your Geont simulations, doing the shielding calculation, and then feeding back and saying, hey, right here, we're a little bit thin. We could be thicker, or right here, the walls are way too thick. What does it look like if we thin them out? So it goes back and forth a little bit. So here's different components and also the materials you end up using. So I mentioned before on this one, we're in Florida, we're not only are we right by the coast, but we're also mainly sand. So here you have a lot of bedrock, so you could go down. We can't really dig down. So our treatment machine, our treatment level is actually on the second floor. But the different materials you use for shielding have different costs. So there's shielding concrete, which is a little more dense, and it costs a little bit more. But on average, the higher density actually gives you a little bit of cost saving. But there's also structural concrete that you're going to use in general, which is different. You don't want everything you're going to build this building out to be shielding concrete. That's not feasible. So you have to know what that structural concrete looks like. And then you're going to have a lot of dirt, particularly if you dig down. You're going to have a lot of dirt or whatever else you have. If your bedrock, maybe it's actually granite or something else that you have there. And you want to use these when you're doing your simulations, because if you don't, then you're throwing away all that information. And again, you're just kind of over shielding. And different things have different costs. And we actually do use dirt and structural concrete as part of the shielding because it's there and it was actually more efficient to do it that way. Just a little aside and some things that were just kind of annoying when the architects would be designing things, they would just kind of end up missing things. There wasn't a roof on the maze, certain things like this. There'd be weird holes in different parts. Just because you get the file, you kind of, you learn really quickly, you get the file, you think it's fine, you run your shielding and you get these weird hot spots. Then you look and it's because there's a big hole in the wall. The architects just didn't actually put anything there. Here, they just have missing pieces in the wall. Sometimes they send you the file and it's the wrong scale. It's just weird things that happen. So you have to just make sure to understand those things. But even though, again, this takes time, it's a little bit here going through there. This time that you spend up front actually saves in the long run. Again, we talked about the different loss points. So in total for this one, there were 55 major loss points to go through. Have to check the vendor of what they give you for those numbers because sometimes they don't make sense. And depending how detailed you want to be, you could actually model the beam lines themselves, the magnets themselves. Again, you lose the beam in the beam line. So if you've ever seen any of these accelerators, there's a beam pipe, right? So there's a vacuum. The beam is going around in a vacuum, and there's a beam pipe that's holding the vacuum, and then the magnets and everything else are outside of those. And when you say there's a beam loss, it's the beam loss out of the beam pipe, right? But then there's all these things around it, like these huge steel magnets and everything else that they're actually interacting with and creating neutrons, etc. So you could take those into account to maybe decrease the amount of shielding concrete you need. So then you could put this all together and come up with the design. Went through many iterations to kind of come to this one and kind of just put it together. I think on the next slide, I have well, I'll wait till we get to that one. Then there's also two key parts. If here's the one where I say you have these large structures. Here's the gantries in the treatment room. So if you look at the one here, this is if you don't take into account the gantry, or you do take into account the gantry. If you don't take it into account, you're going to get a certain result that's not going to be as right. If you take it into account, you'll get a better result. And what you see is when you put the gantry in this large, and here it wasn't exactly the same. So just consider the whole gantry to be iron. It's not 100% iron, but consider it that way. You see what happens is the neutrons get forward scattered. So you have more coming forward. If you don't include it, you don't have as many coming forward, which is very important for your maze design. And secondly, if you do include it, you see that the radiation back here is extremely, extremely low. So there's concrete walls back here. So do these need to be as thick? If you don't consider the gantry, that you may need them a certain size, or whether you do. So this is going back and forth of what you include and what you not include, all mainly so you can get the actual design, the building design, to be as efficient as possible. And the vendors can provide you these CAD for the gantries and the magnets because they have them. So they can give you the CAD. You could bring it into your Monte Carlo simulation and run them. So here's the final thicknesses. We came up here. And you see these are, and we're on the second floor, so there's not dirt outside. We're on the second floor. You see these thicknesses are actually a lot thinner than we've seen some of the other examples. And this is part of that iterative going back and forth, running the simulations, checking and seeing really what's meaningful. And the whole point about this one is, again, if you went from the very first standard design from what the vendor and the architect first come up with standard thicknesses, compared to after you do this iterative design, you can see here we had approximately $1 million of US savings. And this is just because of the amount of concrete saved and also the amount of time it takes to pour all that concrete and the floor space that you gain. So instead of the building being that much bigger because we needed that physical space and having that much more concrete, we were able to save the space. And in this design, there was we had the luxury of being able to move a road, etc. So there wasn't anything large physical except for one building that we couldn't move. But even with that, we were able to reduce the overall footprint, reduce the amount of concrete used to get an overall savings. And remember, these things, the gantries are, go like 3 floors, it goes up, down. So it's a very large volume, as you see here. So we're also able to reduce like the synchrotron, the thickness of the floor in another place because we took into account the dirt that was there for radiation shielding. So all these together, really, it's important because every square foot you save in the space and every dollar you save means where you can spend for better patient care. So these are the final dose distributions. The other part when you're doing the shielding calculations, there's 2 distinct phases. There's the commissioning phase and there's your clinical phase. So clinical phase is when you're actually treating the patients, you're hopefully being able to treat, 3 or 4 patients in each room per hour, 16 hours, getting through a lot of patients. There's the commissioning phase. This is when not only when you're doing the beam, when like the physics team is doing the beam commissioning, getting all the measurements, but also when the vendor is setting it up, right? They got to tune their machine and everything else. So when they're tuning the machine and getting that set up, that is for a short period of time. And depending on which vendor, let's just say that's really one year. It's really usually maybe hopefully 4 or 6 months where they're really having a lot of these loss points. And just to go in a little bit of depth, in the synchrotron system, you had a fast Faraday cup. I skimmed over last time, but you kind of run the beam into this fast Faraday cup to do measurements, energy measurements, dose rate measurements, everything else. And you have a lot of loss during that time. But that's a pretty short amount of time. Maybe that's 4 to 6 months off of a building that you're going to have for, let's say, 25 or 30 years. And if you shield and make the system be able to shield just for those 4 months, you've overspent on your shielding, because there's other things you could do. And for example, I'll show it in a second. I'll skip to the next phase here. So here's the hourly limit. And in some places, we were a little bit higher. Now with the conservative factors that I have put in here, we were actually probably lower. But, there is a part where during the commissioning phase, during this, and for this one, it was actually maybe 3 months, where outside we were actually a little bit higher. But on these processes, during that time, we could set up a very inexpensive fence perimeter so that no one can be close to that building, right? So now you use that distance. So for a short time, there's got to be a barrier up that says people can't come close, and that's going to last about three to 4 weeks. And after that, we don't need it. If we would have actually shielded that wall, the wall would have had to be 3 times thicker. And building a building just for those 3 months and doing that expense didn't make sense. So we went through and talked to the radiation safety officer, everybody else involved, and said, my recommendation is we do this, but we need to take into account these things. And everybody was okay with that. But these are just things you need to know up front. And that's why that design process between the shielding consultant running the calculations, the architect, and the vendor, making sure their numbers are right, is important. And then there's other considerations. There's the air ducts. There's always penetrations in the room. You need air conditioning. You need wires going through all these things. So you need to take those into account. So usually after we got to the full design where we were comfortable, then put all the penetrations in and run that and see if anything happens. And as long as the penetrations are done right, meaning they have a couple extra bends, you never have a straight line, etc. There was no issue with those penetrations. The other thing is sometimes there's temporary wall areas. So you build the building, and then you got to get all this equipment into the building, right? The equipment doesn't exist, and you build the building around it. You build the building, then you bring in all these big components, like we saw, the big semi bringing in that big cyclotron to come in. Well, it needs a place to go in, and that's usually a temporary wall. So you have a big opening, it comes in, and then you kind of go and you put in more in brick instead of a slab going through. So particularly for a cyclotron, you have to do those calculations carefully because there could be little gaps to go through. But when we did that for ours here, there was just a minor difference between if we did have him or not have him. So it was a good design of how we put this together. But these are just some things you have to consider. Some other things that could be cost savings and also space savings. We talked about the mazes, and I actually believe in some of the photon clinics here, you don't actually have the maze, you have a direct shielded door. So the shielding design that we have through here, we don't actually need a door to shield. There's no radiation coming out from there. It's just to have it closed and open so that someone doesn't walk in. But you could have these direct shield doors that kind of open and close that actually act as part of the shielding. And if you do that, you could save physical space. Those doors are, expensive, but you do the cost benefit. When we looked at it, it would have been a little bit cheaper to go with the doors, but then when we thought about the long-term maintenance and everything with it, we went ahead and stuck with the maze. All right, so that's kind of going through, even though that one part, the shielding calculations and all that is actually, I think we ended up spending maybe a total from beginning to end, maybe 6 months, maybe 9 months, depending when we consider start and finish. The actual iteration with the architects and stuff, that was probably a couple months through, but getting everything set up. But again, doing that right, doing it up front, spending that time does have savings, not only the direct cost savings that we can actually calculate, but just the square footage and being able to have a little bit more space within the treatment rooms, et cetera, I think is probably even more valuable than the actual cost savings. The other thing you have to consider is then the monitoring. So in Linux, in the photon rooms, you have these monitors that, the radiation on or off, and they're actually detecting photons. You usually don't have a neutron monitor in there. Maybe if you do a lot of the 18 MV ones, you may have a neutron monitor, but probably not. Again, with particle beam, what you're shielding neutrons. You're shielding for those neutrons. So you usually do have the neutron detectors in there. Again, this is just the regular safety so that it can be able to detect whether the beam's on, know how much background radiation there is. You do all the shielding calculations we know that there's going to be virtually no extra background radiation. We know the the decays of the things in the concrete, etc. But you always need those just in case. Maybe something is left in there that gets hot, these different things. So you always have your radiation safety monitors. Here's a sample of, the system that we will be setting up. Okay, so that was the portion on the kind of on the regulatory side and some of the shielding. I put some of the numbers there that we use in the US. I think they're probably going to be the exact same here. If anything, they're probably even more probably lower here than they are in the US. So it's fairly straightforward. Nothing really different about these machines. You have to think about neutrons as opposed to photons, but besides that, I think everything else is straightforward. There was a overheard, even though I could pick up the word decommissioning. So you do have to worry about with these systems maybe later, 20 years when they're done, or with parts coming out. Are they radioactive? Did they get hot from all this neutron contamination? So that's something that you do have to think about a little bit more with cyclotron systems because of that energy degrader and everything. With cyclotron systems, there's actually no component that gets extra hot because in general they are cleaner. They have a bigger footprint, but in general they're cleaner in that aspect. The concrete does get activated, but those usually tend to decay fairly quickly. So those are the kind of things to think about during the decommissioning phase. But again, these buildings and these major pieces of equipment will probably be installed for at least, hopefully, 20 plus years. You're not like a Linac, you put them in and then 10 years later, take it out, put another one in. Okay. So now a little bit more on the some of the physics and some of that on the biology aspect, since it is proton therapy and a little bit of for the carbon therapy. So we had this one earlier. Protons at this bright peak do interact slightly different than photons do. So they do have a higher LET, the linear energy transfer. So what this is, and many talk about this again on the calling it still in the physics aspect, because this really is about how the interactions are happening. What is the physical interactions happening that leads to then the biology? So a common term is this RBE, relative biological effectiveness. Usually it's your photons, but it's any reference radiation. And then whatever you're doing, protons or ions at the bottom. And basically you give a certain endpoint and you say, well, how much more effective? So for 10% cell kill, how much more effective is this form, the proton or the ion, compared to the traditional one? And in this cartoonish example, which that's a real example, but anyways, here, you get it, that's 1.5. For 10% effect, you get 1.5 or 50% more kill. And it's the same amount of radiation, but it really is coming from how the radiation is being transferred, how the energy is being transferred. And there's different parts. So a particle beam has a spectrum of linear energy transfer. It's in units of keV per micron. And putting this on under the physics and not under a biology aspect, because this is really the physics part of how the particles, whether it's proton or carbon, interact with a material that then leads to some different biology aspect happening. But if you don't understand the physics of it and what's happening there, then you can't really know then the biology and everything else that happens afterwards. So you have a way the energy is being transferred. And then depending on your fractionation, so before we talked about you give a little bit every day, you do that to give chance for your normal tissues to repair a bit. So how that happens relative to the interaction is different. This quantity, LET, or this keV per micron, you get different interactions with cells depending on your ion species. So a proton at the bright peak, they may have 10 keV per micron, and a carbon beam at an entrance that has about 10 keV per micron. Though they have that same physical unit, the biology is going to be different. And the reason for that is then deeper into the interactions, not the cellular interactions, but the physical interactions of how that energy spectrum is being transferred. So that's why that part is really key. And also mentioning this, since part of this is you want it to be a research park and different things to look at. There's still a lot of the physics here on the energy transfer. There's a lot of work to be done there and a lot of research to look into. Uh, so describe the action of radiation and matter as opposed to, and so it's that transfer, not just the macroscopic, how much energy was transferred, but how it's actually being transferred. So here's an example, and this is actually taken from ICRU, this picture, so you can always look this one up. But you can think of low LET, photons are low LET, just on average, the radiation that we deal with a 6 MV or 10 MV beam. Those are give about 0.5, 0.6 kV per micron, this unit. Protons give about 1 to maybe at the most 10 kV per micron, right at that bright peak. So we'll just consider them being low LET. Carbon is like medium LET, 100 kV per micron. Again, it varies. And then I put this in here again for this very high LET, this 200 kV per micron. And mainly that's in your overkill effect. So this is a track structure Monte Carlo kind of showing. The key on this one is that this is kind of describing it's the same amount of energy being given, but you can see it's being transferred in a different way. And maybe this one will show a little bit better. So again, here's photons or protons hitting now on the size of the cell. This is like coming back. This is you might think this more on biology, but still being a physicist, thinking more looking at it more on the physics perspective. We still need to be able to do these measurements down to micron size or maybe even the nano size. Because a lot of the things that are done here, again, mentioning it because if there is going to be a branch of research that's going to happen here in this research park that you're building, and since we're, at the Center for Atoms for Peace here, doing more of the nuclear physics, a lot of these interactions in general models exist and such, but actually detailed measurements don't really exist. Dosimeters or monitors or ways to measure these more precisely don't actually really exist well. So these are based on simulations, based on the models that we have and such, but getting good measurements is still very important. So slide aside, but here's low LET, a medium LET here, saying carbon. And what this is kind of showing is that in here in the size of the cell, photon radiation, and to some extent protons, but protons slightly different, give a very uniform distribution. Whereas if you have this medium LET, so you could think of this as a carbon, or even at the Bragg peak for protons, to some extent, now you go, instead of looking at the micron level, maybe 10 microns, now look in the nano, maybe, 10, 50 nanometers, you see these large spikes of the energy being transferred. And that leads to different kind of cell damage, more effective damage. So again, it's still the same amount of the energy. So it's still the same grade, that joules per kilogram, still the same amount of joules that are going in. It's just how it's being transferred is different. And I'll show in a bit, but there's no good real detectors, not talking more on the physics side, to actually measure these. So these are all simulations, based on models that are pretty good, but actual, getting things more refined don't really exist. But these large peaks then are more effective at killing the cell, that then leads to these different things and that high biological effectiveness. So just showing it again, that here you have the cell, and now we're talking about on the DNA level. So, we're used to talking in radiation therapy about, again, grade, these joules per kilogram, and even you just say it's per kilogram. Kilogram is pretty big, right? Okay, that's a big chunk of matter. Even if you could take that down to, maybe a small voxel that's like 2 millimeters by 2 millimeters by 2 millimeters, okay, it still makes sense to talk about gray joules per the kilogram there. But now when you're talking about a cellular level, now you're talking about microns, or you're talking about DNA level, where you're talking about nanometers. But talking about even talking about a joule in a nanometer sense doesn't make physical sense. So understanding what's actually happening at that level is very important. Uh, so again, low energy, you could have a single strand break. This cartoon isn't that great, but it kind of gives an example where these medium LETs, you have these huge breaks. And what basically happens is then the cell can't repair itself. If it's simple breaks, the cell can repair itself. So you don't kill as effectively. But if you do it like this, then, it can't repair itself. It will die. And that's where you see this different biological effectiveness. The other things that to kind of understand is there's a lot of the biology aspect here, but part of this is, for example, there's a thing called oxygen enhancement ratio. So traditional radiation therapy is an indirect mechanism. You kind of ionize and you create a free radical, and that actually damages DNA, etc. As opposed to particles, even with protons and carbon, that's a directly ionizing. You're actually damaging it directly. Well, if you damage it directly, then the indirect method uses oxygen as a transport. You're kind of ionizing, you're getting this free radical, and that's actually doing the damage. And unfortunately, a lot of tumors, particularly in general, you may hear some things that say they're resistant to radiation, tumors resistant radiation. Actually, if it's resistant to radiation, it's actually also resistant to chemotherapy and probably is also hard for surgery. The reason for that is there's not much blood flow getting in, so there's not much oxygen, but the cells are still alive, so you can't effectively kill it. And so that oxygen enhancement ratio is saying that you need, for these more traditional photon therapy, you need that oxygen, so it needs to be a well-oxygenated tumor, meaning good blood flow in there, in order to damage it. Well, for a higher LET, maybe the Bragg peak of the proton or in carbon, you don't need that oxygen there. So these things are radiation resistant because they are hypoxygen, not much oxygen there. You don't need that oxygen enhancement ratio. You can actually damage it. So again, on the physics parts, knowing those interactions and knowing how things are actually damaging cells or interacting is important to know. And there's different parts to it, but that's more on the biology side. The other thing, when said protons, we do a lot on protons, the re-radiation. We heard that earlier. Part of that is because we said protons can spare a lot of the normal tissue. So if you already had radiation and your spinal cord already got radiation, you can't really give any more to it. So you need something that can spare it. The other thing that happens when a tumor comes back, it generally becomes radiation resistant. So that means that it's kind of either through the cell cycle such, the photon radiation doesn't have as much effect, but again, more of this high LET does have an effect. So radiation resistant tumor, this re-radiation, hypoxic means low oxygen and such. These type of treatments are much better for. Again, here's just the model of, here's the traditional photon beam with the exit and entrance dose and how you make a Bragg peak. And this one is just showing for carbon, you get this large biological enhancement, factor of 3 or so. Protons, we generally use a 1.1, but in the talk earlier, he said, he did mention a little bit about LET optimization. This is where you're trying to use the computational software to try to get that higher LET into the tumor. And that's so you can kind of take advantage of this. Here's part of the microdosimetry. So part of the physics 2 talk here is for proton therapy, this spectrum right here, this is actually that microdosimetric spectrum. So we usually use a number like 5 kV per micron. What that is that's actually the spectrum, kind of like the average value. Here's a microdosimeter. There's also tissue equivalent proportional counters. but they all have certain thresholds. They all have their limitations. Uh, so we generally do the simulations and we come out and we can infer what the spectrum is, but it's always good to kind of measure and get better detectors so we could understand better what's happening. But essentially, this spectrum is what's actually this is actually the energy being transferred to cell in a certain way. And this leads to the different kind of cell kill. And this is for protons in different parts of the Bragg curve. So in the entrance versus in the peak. So you can see that difference. In carbon, these spectrums will be more over here. So these are some of the detectors that are used kind of to represent what actually a cell is being received. So they're a micro, so they're more in the micron size. And again, kind of going through of the cellular level versus the tissue level. Reason to say that is because we've been talking about how things damage in this aspect, and you could do this with cell measurements. And here's these are some of my former graduate student and postdocs and such. But this is a good example of this right here, D1 through D4. These are different depths along the Bragg curve. So these all have the same amount of radiation, 5 gray, 5 joules per kilogram. That's what this one was. Each of these dishes got 5 gray, but they were just different points along the Bragg curve here. So different LAT spectrum. And you could like this one because it's a clear visual of definitely there's not much more cell killing happening here than there was here. So there is a difference. And the difference is in this macroscopic thing we talk about the amount of energy, but it's really how that energy is being transferred. And you can do it for different cell lines and such. And here's the same study. So here I met Ostron doing some cell work on the weekend there. And this is for carbon, and these are some of the carbon data getting. Again, X-ray versus carbon. Again, so the physics is what's leading to this, the way the energy is being transferred. But when you look at this, and for those that have a little bit of the radiation biology, maybe some of the medical physicists or the physicians, you see that the photon has a shoulder, right? And this shoulder, this kind of curvy part here, this is what you take advantage of when you're doing this fractionation, so that it gives the normal tissue a little more time to repair as opposed to the tumor. But you see, on average, when you're doing with high LAT, like a carbon, and maybe for proton, you don't really have that shoulder. It's really kind of straight. So fractionation makes a little bit less sense in carbon therapy or a high LAT proton therapy. So knowing the physics of this one and the biology aspects leads to how you may want to end up treating a patient. And that was the cellular part. And then, to do more in the tissue and organ, again, going through, this is just talking about some mouse studies I've done. A reason to bring this up again is, again, you're building this research park. So what kind of research are you going to actually want to be doing? And if that is a big component, so, it's a question, how important is that research aspect, not just a clinical trial aspect, maybe some of this more basic or translational, that might lead you to say how you want your system designed or what you want actually out of that system. And here's just again, when we do some of the animal studies, and this is proton, just showing the difference between the different kinds of treatments, and you could get an actual big effect there. So this has been published just to go through, but again, these are different portions, and all these go into then modeling. So how, again, in the research aspect, you could do these studies, and the reason we want to do the studies is so then we can do more effective treatments for the patients. So then the physician, the radiation oncologist, can design a trial based on this kind of data to get the best effect for the patients, and that then becomes your biophysical models here. And this is just different ones. So you could do, having a model is great, but if you can't actually do a meaningful computation, then it's not too useful, particularly if you're going to do it for a trial. Again, you want to be able to treat a lot of patients. You need to be able to do things that are computationally efficient. Okay. So that was the discussion of the regulatory kind of the shielding aspects and some of the I called it physics part two, kind of more of the physics and biology aspects than the basic physics. So any questions on this one? I know it was after lunch, so it's a hard lecture to do after lunch. No questions. Good. We can.
So is a shielding or radiation protection difference between techniques like old technique IMRT, IMPT or proton arc?
Yeah. So from proton arc, proton arc versus IMPT, you can kind of think of it the same as the photon radiation arc versus IMRT. Uh, both very similar. The main thing is if you are doing the arcs, you are going all the way around. So you just have to be concerned a little bit more about where your primary shielding is around instead of mainly doing, posterior or lateral beams. But generally, when we treat, just as in photon therapy, when you treat the IMRT, you're actually coming from all angles. So you are kind of doing arc as just separate. So in the shielding aspect, there's not much. What would be a difference is if I didn't talk anything about if we were doing like a flash therapy. So that could be something different because of the any 1 hour aspect. Um, but as far as a standard IMPT versus an ARC, they're going to be very similar because it's still the same volume you're treating. The amount of radiation you're giving is going to be basically the same. Double scatter and spot scanning are very different, but any modern system wouldn't be doing anything in the double scatter. The only thing I'll say on that one is unless you're doing eye treatments, but then your energy is a lot lower. So generally, if you're shielded for regular treatments, and then you end up doing a lot of eye treatments, you'll still be well shielded for that because the energy is just that much lower that you use. But I didn't say anything about eye treatments or that part, so I just wanted to mention that as an aside.
So the flash treatment gonna need more shielding.
Yeah, so for flashes, again, it depends then really at the end because there's the main regulatory that comes out is in any 1 hour. So at the beginning, there's the regulation about it has to be below a certain amount, and here you'll have some number below X amount in any 1 hour. There's a weekly and annual, but when you take them all into account, it's really that in any 1 hour usually is the major component, the one that's really driving. So now in Flash, the idea of a Flash for those that may not is you're doing a really, really high dose rate. So maybe 40 gray per second, maybe at 60 gray per second, whatever the number is. Okay, and you're giving that, and let's just assume we're at the point that you could do that volumetrically right now. Doing a full volume that isn't just really really small isn't feasible right now. But let's say you got to a point that you could do a volume on like a quarter of a liter, and you do that very fast. The regulation is still in any 1 hour, but then you have to really think about not just meaning the regulation. You got to think if I did that within one minute, what is the radiation outside? Are we still protected enough? And you could do those kind of calculations, and that's come when we did the calculations. Even though we weren't thinking necessarily that we would do flash day one, it was always in the back of our head that maybe at one point we would be doing some flash therapy. So if we take into account, again, we're going to do 50 gray per second, but each treatment then is going to be just, one treatment because then you still have the time it takes to get the patient in, IGRT, get them out. So looking at that, we didn't see that there was any real difference needed for shielding because I did the shielding at that, assuming every patient was going to get one fraction of 50 gray. Okay. And that was a conservative estimate, but flash was in the back of my head thinking, 2035, maybe we are doing flash for everybody because it becomes this miracle thing and it is really good. So I didn't directly do it, but that was part of why I used 50 gray one fraction, was thinking if we did do flash, that's kind of the thought, right? Is you do few number of fractions, very high dose rate. So again, you could put it in and have that thought process when you're doing the shielding calculations. It just as the next question. The only thing I don't know, because I don't think anybody knows about flash, what a standard treatment would look like for flash. So,
I have one question about the neutron contamination. Do we need to monitor, all the area of the...
Yeah, and that's why it'll probably take me to, let's see if I can. Boom. So this right here. So in every treatment room and in the beam line, so in your regular photon vaults, you have this thing. And you probably have this and a this and maybe a this. So this is a photon monitor, right? And measuring if there's photon radiation. This is a neutron monitor. So this one isn't, and this one for the radiation protection.
Yeah.
This one isn't monitoring like the exact energy spectrum stuff, not made for dosimetry. That's more of these Wendy detectors, and I guess I didn't put one in here. I should have done that part. But this you will have. You should put them in every treatment room, in the beam line, and in the synchrotron room. And if there is a high level of neutrons, obviously when the beam's on, right? These aren't on, because when the beam's on, neutrons are being created. But once the beam turns off, that neutron dose falls off really quickly. This would pick up if there's some background, something got contaminated and is creating a lot of neutrons. These would pick it up. So usually these are kind of, prominent, maybe where a therapist would walk or something like that. But yeah, that's what this one is for, to pick up that.
The last question, is there any explosion within the synchrotron or accelerator room?
Any what?
And any chance of explosion?
Explosion?
Yeah.
So that's a good question. So the answer is no. The only thing is depending on your source. So for example, Mayo Clinic, we have a Mayo Clinic in Minnesota, in Arizona, and in Florida. In Arizona, they were very concerned about, in Minnesota, we have a gas, a helium gas, the tank. They were really concerned about that in Arizona, and that was the state regulator, right? So different state, different regulatory body. So the source had to be different. They didn't want the source to be a helium tank. So we had to get a different source. Fine, you just do that. It's not an issue, but it was a thing. So, I mean, many places have used the the hydrogen gas bottle, and it's been fine. But if the regulator is concerned that is something, or they've already made a decision before that they don't want that to be present in a hospital, then you have to use a different source. But so that's the only one. I don't think it's a real risk because I've never ever heard of it happening. Many proton centers, they all use that one, but there has been in the US, some states, and I don't know about internationally, but some states have said they don't want the hydrogen canister. They do something else.
Okay, thank you.
Just a quick question. So on the regulatory body side, which part should we concern the most?
The first part?
Which part that should the regulatory body should be concerned?
Oh, for the regulatory body?
Yes.
So neutron contamination. So is there anything? So, okay, when the patient is in the room, they're getting irradiated. They're getting radiation. Once the patient leaves the room and you have a radiation worker go in, are there things that are going to be contaminated? Is there anything that's going to be quote unquote hot in there that the radiation therapist might come into contact with? For example, before in the first lecture, I kind of skipped over the whole double scatter, but they're used to have these double scatter, you come out with a big fluence of protons, kind of like a photon treatment. There's all these protons coming, and then you put these big brass apertures. It's a big hunk of brass to kind of collimate the beam, so only if some protons go through. And then you had a modulator kind of to shape the beam. Those things would get hot. So you were putting a lot of protons in them, and it's brass, it get hot. So there, as a regulator, you should be concerned about, well, someone has to pick these up, someone has to hold them, someone has to carry them and put them in, and they have to get decontaminated. They have to go in a secure place for a while to cool down. That is something very very important to know about. In modern, the spot scanning, that part isn't really there. There's no, most systems, because I don't know about every single system. Most systems don't have a component that gets really hot. There could be, you could design a system that could get hot in certain ways. So knowing if, and that's why doing the radiation shielding, because any source of neutrons is going to be a portion, right? So you have your controlled and uncontrolled areas. So you just have to make sure that even your controlled areas, that the exposure is below a certain amount. But those would be the things I'd be concerned about. So, as a regulator, asked the center, are you going to do any aperture-based treatments? And not even double scatter. You could do an aperture-based treatment for brains. Just talk about spot size a little bit to get a really tight penumbra, to get a really sharp beam. You may do an aperture. So you may have brass collimators there. And if you're going to do a lot of, let's say, stereotactic brain treatments, just make something up, then you may have these apertures that are going to be hot. Then as a regulator, you want to know, how are you going to be handling them? How hot are they going to get? What energies are you going to be hitting with? How hard are they going to get? Where you're going to store them, etc. Make sure they're securely stored and stuff like that. So knowing as a regulator, are you going to do these type of treatments? So you can do anything aperture based, or aperture or collimator based, however you want to phrase it. Are you going to do the eye treatments aren't so bad because it's very low energy. So those things don't get really hot. But there could be treatments that you do that you will use a secondary device that may get activated. The other part, since on the regulatory part, it's not so much a case for the synchrotrons, but for the cyclotrons. The cyclotrons themselves get hot. So, kind of describe the beam going around, right? As the beam's going around, there's also a lot of beam getting lost in there. Then all the beam doesn't perfectly go around and so a lot of it's getting lost. And when you extract it, a lot gets lost right there. And then we talked about the double scatter part where you're creating all that, and that's creating a lot. So as a regulator, you probably need to have some rule or some information about, because sometimes somebody has to go in to that. Something's going to happen. Something's going to break. It might not even that, but something else will break and they have to go in. So you have to have some rules already set up to knowing how hot is that thing going to be. How long can the person be in there? I mean, they have to have the radiation and everything, but before anybody goes in or just monitored, you should have your rule set up of how much they can get, all right? Because they may have to go in. So maybe that one, they're going to exceed their thing for that day or for that week. But then regulatory wise, that person cannot go back into that room for a month or whatever the rule is going to be, right? So as a regulator, knowing that system or which parts of the system are going to get hot, and the people that go in there that have the right equipment, right? They go wear a ring badge, this badge, what do they go? And it's neutrons, worried about neutrons, right? We're not worried about photons. So do they have even the proper monitor to go in? Do you go in with the survey monitor, with the Wendy monitor to go in, measure the dose rate, these kind of things? So the general thing of what is going to be hot, right? After the beam's off, no radiation is produced, what components are going to be hot? For a synchrotron spot scanning, the answer is basically nothing. But for scatter system, aperture-based system, those things will be hot. Or for cyclotron, the cyclotron itself or the degrader is going to be hot. So knowing that part. So long answer to her. The first thing was nothing, but really there's all these other things, yes. No. No other questions? Right, I think next on the agenda is like a 10-minute break and then another one. Yeah.